This is our second example of looking at the second fundamental theorem and how it comes into play when you're doing something graphically. So we have h of x equals the integral from 0 to x of f of t dt, where f is a continuous function with domain 0 to 12. So we have 0 right here and 12 out here. And while we're at it, I'm going to mark this x value. So it's 1, 2, 3, 4, 5, 6. X equals 6. It's also important to note that you weren't given the actual equation, and it's not something geometric that you can just find an easy area of. So this is a different kind of question. So sometimes students think, well, how am I supposed to find h of anything if I can't find the area? But look what they actually asked you for. H of 0 means h of x, this x gets replaced with 0. So does this. So this is the integral from 0 to 0 of f of t dt. Well, this area has no width, so there is no area, and h of 0 is 0. So they're actually giving you a point on the graph on the original function h. Alright, so part B says, on what intervals of x is h increasing? Justify your answer. Well, I already know the justification without even thinking about it. We've done this so many times, but h is increasing when h prime of x, the derivative, is greater than 0. The slope is positive. So I know I need h prime. I come over here and I'm like, well, h of x is equal to the integral from 0 to x of f of t dt. And we're going to use the second fundamental theorem. We're doing the derivative of an integral. And h prime of x equals f of x. We would take the antiderivative, plug in x, plug in 0, subtract, take the derivative, and we're back with what we started with, but with a variable swap. So this is actually, this graph right here is our h prime of x. So when is h prime of x greater than 0? Well, that would be from 0 to 6. Okay, so on what intervals of x is h concave up? Well, h is concave up when the second derivative is positive, which means the first derivative, what we actually have, h prime of x, is increasing. So we're looking for when this graph is going up. And this graph is going up from 9 to 12. So the next question is h of 12 positive or negative? Explain. Well, we know we started at a y value of 0. And if you look, the graph had to be increasing from 0 to 6 because h prime is positive. And the area represents the net change in h. So it's actually gained a pretty good sized amount of area. So we've had a good net change in h. Then from 6 to 12, the graph was decreasing. But if you compare the two areas, this area is much smaller than this area, so the graph was increasing a lot more than it was decreasing. So we know that h of 12 is positive. And again, for the reasoning, I would say that the integral from 0 to 6 of my f of t dt is greater than the integral from 6 to 12 of f of t dt. Okay, the last question for this one, it says, for what values of x does h achieve its maximum and minimum values? Justify your answer. So it's actually looking for absolute extrema, and we know that absolute extrema take place at endpoints. And we're doing the candidates test here. So x equals 0 and 12, and critical numbers. Should be or critical numbers. And we have one right here. It's at x equals 6. So the question is, which of these is the greatest and which is the smallest? We're comparing h of 0, h of 6, and h of 12. Well, we know what h of 0 is actually equal to. It's the integral from 0 to 0, so that's 0. Now, I know that h of 6 equals the integral from 0 to 6 of f of t dt. And I know that that is greater than 0 because the graph was increasing from 0 to 6. So, h of 12 equals the integral from 0 to 6 of f of t dt plus the integral from 6 to 12 of f of t dt. And there are all different kinds of ways you can say this. I know that this was greater than 0. I also know that this integral, so I know that the integral from 6 to 12 of f of t dt is less than 0, but I also know that it's actually less than this. So I'm going to put that in there as well. I'm going to say that the integral from 0 to 6 of f of t dt, and I'm going to look at the absolute value of this, is greater than the integral from 6 to 12 of the absolute value of my f of t dt. So what that means is, while this is greater than 0, this is also greater than 0, but we have subtracted out a piece right here. So we've taken our area, the original area, and we've subtracted some. So this has to be larger than all of this. So it says, for what values of x? We know that there is a min at x equals 0 and a max at x equals 6. Now I know that this is the min because of this right here. This is greater than this, so our positive piece is overwhelming our negative piece, so we're going to still end up with something positive out at the end. And I know that it's bigger at 6 than 12 because we are subtracting a piece out here. So I think words would be a great help when actually writing this justification. You could write out the logic and make it make sense. I'm not going to do that here, but literally that's all you need to do is just write down, say, well, at 6 we know that the area is positive and it's bigger than the area from 6 to 12, which is negative. Therefore, this number will be greater than that number, but we also know that this number will actually be positive because this is less than this in magnitude, meaning that this is the smallest number, this is the biggest number.